In this video you will learn how to properly connect two LEDs on a breadboard to each other in parallel to a battery. You will learn here how to use a multimeter to measure the voltage drop across the LEDs and also across the resistors, which we will use to protect the LED, and how you can use the characteristic curve of the LED and also Ohm's law to limit current flow to a safe value. And finally, as always, there's going to be a summary of the most important facts from the video for you at the end, so stay tuned. And my name is Andreas from The Fearless Engineer, and here we go. Now, the major goal of this experiment is to limit the current flow through this LED here by selecting an appropriate resistor which we put in series to it. And the LED is going to be powered by a 9-volt battery, which you can see here. And in a previous video we have already seen that the current flow provided by this battery, when we connect it directly to the connector pins of the LED, is far too high, and the LED is going to be destroyed. And this is what we want to avoid here. And we also want to go one step further. We want to carefully control the amount of current running through the LED. In practice, this is often done to control the lifetime of the LED, because if the current flow exceeds a certain threshold over time, this is going to severely affect the lifetime of the diode. And typically in most applications, the current flow is somewhere around 20-25 milliamps. Up until, let's say, 40 milliamps, everything is still going to be fine, even though 40 milliamps is unusually high for an LED, but I think 25 is a good setting. And we have shown before in a small calculation that if we connected an ohmic resistor in series to an LED, that this will limit the current flow to 25 milliamps if we connect it to a 9-volt voltage source. And this blue box here on the left side, this is an ohmic resistor which can be very finely adjusted to a certain value. And as you can see here, you have all these switches, and if I flip a certain number of these switches here, now everything is set to 0. This means the setting is, or the overall resistance value of this box here is 0 ohms. And if I wanted to, let's say, select 360 ohms, just as we have arrived at in the calculation previously, I have to flip the 300 switch, I have to flip the 40 switch, and I also have to flip the 20 switch. And now I have 360 ohms which are available between the two connector openings here, which I can now connect into my circuit. And this is what I have done on the small breadboard here, which you can see. We have discussed breadboards before in another video, and this breadboard is being connected directly to the power source via the power rails. The positive terminal of the battery is connected up here, the negative terminal is connected down below on the blue power rail, and in between right now there is no LED. We are now directly connecting the resistor box to the current meter here, and the idea of this current meter is to give us a measurement of the current flow through this entire circuit, so we can check whether we have used Ohm's law correctly. And now let's close the circuit by connecting this pin here. And as you can see, the current flow which has been measured now is at 24.6 milliamps. And given the result of our calculation, which is 25 milliamps, we are pretty close here. And also note that we have to take into account a certain tolerance of this resistor box here, as well as the resistivity of all the connectors in the breadboard, in the cables, and so on and so forth. So the fact that this is not exactly 25 milliamps, but a little bit below, this is perfectly normal. So our calculation was made correctly. And if you take a look at this breadboard here, we have this small blue bridge here. This is the placeholder where we want to connect the light emitting diode now. So let's pull this out here. And now let's insert the LED. You have to be careful to connect the longer leg to the positive terminal of the battery. So a positive terminal is here on this side. Let's make a little bit of room. Now let's enter the LED directly into the positive power rail, as well as this white connector here. It's lit up, so everything is working fine. And if you take a look at the current measurement, the current flow now has dropped to 18.7170 milliamps. So this means, according to Ohm's law, that the overall resistance of this series circuit here, because the LED is in series to the resistor, now has increased. And decrease in current flow means an increase in resistance. And this is to be expected since the resistance value of the LED is not zero, but it has a certain value according to the current voltage characteristic. And we have measured the current voltage characteristic of an LED before, and we have seen that once the initial threshold is exceeded, the current flow increases strongly, but at 25 milliamps or around 20, 25, 30 milliamps, we still have a significant resistance. And if we look into the measurement curve of the experiment which we conducted in a previous video, we can expect that at around 25 milliamps, 20 milliamps, the resistance of the LED is at about 80, 85 ohms roughly. And this means that we now have connected an 80 ohm, 90 ohm resistor in series to the 360 ohm resistor, which explains this decrease in current flow. So for you, this means if you perform the calculation of the resistance value which is needed to control the current through an LED, what you have to do is you have to calculate the amount of current without the LED, since in many cases you do not know the exact characteristic of the LED. And this means you have selected a resistance value which is a safe margin away from a problematic current, because the resistance value has given you the calculation using only the resistor has given you the upper limit of current to be expected in case you have an LED of perfect conductance, which is never the case. The LED always has a certain resistance value. So it will never exceed 25 milliamps. If you want to increase the brightness, what you have to do is you can take into account the expected resistance value of the LED. Let's say we expect the LED to have 80 ohms of resistance. What we can do is we can decrease the overall resistance of the resistor which we put in series to the LED by 80 ohms, which would in this case mean let's go from 300 ohms to 200. Let's go from 360 ohms to 280 ohms and see what happens to the current. Let's switch on 200. Now we have 200, 240, 270, and let's go to 280 now. And as you can see, the current flow has increased to 24.1 milliamps. And maybe you noted that before I flipped the 10 ohm switch, the current flow was exactly at 25, almost exactly at 25 milliamps. So what we can deduce from this experiment here is that the resistance value of this LED is at around 100 ohms. This is the value which we get if we set this resistor box here to 200, 240, 260, 260 ohms, which is 100 ohms less than without the LED, which generated also a current flow of 25 milliamps. So 360 minus 100 gives you the setting which we have now set on the box. And this experiment shows you that by using Ohm's law gives you a safety margin, and after entering the actual LED into the circuit, you add a few extra ohms which you have to take into account for in terms of current flow, and powering an LED at, let's say, 18 milliamps is still sufficient for a decent brightness. But in case you really need to exploit the brightness and you really have to go up until, let's say, the full 25 milliamps, you can always slightly decrease the resistance value which you have computed before. Now let's summarize the most important takeaways from this video for you. Firstly, in this video you have learned how to easily connect two LEDs in parallel to each other on a breadboard. You also know now that a green LED has a lower voltage drop across its connectors than a red LED. And thirdly, in measurements we have seen that the reduced voltage drop across the LED leads to an increased voltage drop across the resistor which we have connected in series to it, and vice versa. And with the help of LED characteristic curves and also Ohm's law, you can now calculate how large a resistor which you connect in series to the LED must be in order to limit the current flow through the light emitting diode to a safe value. That's all from me for now for this video. If you have any questions, leave a comment down below. Also suggestions for future videos should go there. Have a nice day. See you next time here on The Fearless Engineer.